Hello, my name is TC Fraser and I am a PhD student at the Perimeter Institute for Theoretical Physics. My talk is based on some forthcoming work that will be available in the near future. If you're interested in learning more, please feel free to send me an email. The purpose of this talk is to explain how techniques from estimation theory can be utilized to tackle something called the quantum marginals problem. For those that are unfamiliar with the quantum marginals problem, consider a tripartite quantum state on three subsystems labeled A, B, and C. From a joint state, it's easy to calculate its marginals. You simply just perform the partial trace over each of its subsystems. But the reverse of this process is much harder. Given a collection of marginals, can you calculate a joint state which produces those marginals? Such a joint state may or may not exist. If it does exist, then we say that the collection of marginals is compatible, but otherwise they're incompatible. The objective of the quantum marginals problem is to characterize the space of compatible marginals. As you can imagine, the quantum marginals problem appears in many situations involving multipartite quantum systems, including entanglement theory, quantum causal modeling, quantum matter, and so on. It is also well known that the quantum marginals problem is very hard. In fact, the general problem is known to be QMA complete. Nevertheless, substantial progress has been made by Kliatchko, at least in the restricted setting where none of the marginals under consideration are overlapping. So the purpose of this talk is to outline a general method for tackling these marginal problems that is applicable to finite dimensional Hilbert spaces and arbitrary collections of marginals of any size regardless of their overlap. This method is largely inspired by the work of Christandl and his colleagues and is fairly simple to understand. So first you begin by sampling a joint quantum state according to some suitably chosen probability measure. Then, given that quantum state, you independently prepare many identical copies of it, and then finally perform some measurements on those copies in order to extract estimates for each of the marginals of interest. The point of this approach is to examine the resulting sequence of probability measures over the space of possible estimates for the marginals, which I'll denote eta sub k. On one hand, if the probability for a bad estimate can be made sufficiently low, then the probability of producing incompatible marginals should also be low. On the other hand, if the prior probability measure is suitably chosen, then the probability of producing compatible marginals should be reasonably high. Unfortunately, we immediately encounter a familiar problem. It's that the measurements which produce these estimates for at least overlapping marginals do not commute in general. Therefore, these measurements cannot be performed simultaneously. Fortunately, when working in the setting of independently and identically distributed sources, non-commuting operators are not a problem. So to bypass this problem, you simply prepare the joint state 3k times instead of k times, and then extract an estimate for each marginal by performing the corresponding measurements on disjoint blocks of size k. Moreover, if each of the individual estimation schemes satisfies a large deviation principle, then so will the tensor product estimation scheme. Therefore, we can ensure that the error probabilities decay to zero at an exponential rate. Finally, as we already mentioned, you can eliminate this explicit dependence on the joint quantum state by sampling it randomly with respect to a prior measure nu. Of course, for the overall technique to work, it needs to be that every collection of compatible marginals has a decent chance of being estimated. Therefore, we must pick a measure nu which satisfies an extra condition to ensure that this is the case. Luckily, the Hilbert-Schmidt measure is an example of such a measure. So with all these ingredients in place, it is possible to show that the asymptotics of these eta probability measures encode whether or not a collection of marginals is compatible, thus providing a solution to the quantum marginals problem. Loosely speaking, it can be shown that these measures will decay rapidly when their arguments are incompatible, and remain reasonably large when their arguments are compatible. Unfortunately, this technique is a bit blind to the case where the marginals are on the boundary between the compatible and incompatible regions. So in conclusion, I provided a method for characterizing the space of marginals that are compatible with some tripartite quantum state. But moreover, it should be clear that this method trivially generalizes to marginal problems for any number of parties as it bypasses the difficulties associated with overlapping systems. The specific estimation schemes I've been referring to can be found in Keel's paper. But in my paper, I'm going to additionally discuss various ways in which these distributions can be calculated analytically and show that these calculations rely heavily on representation theories of the symmetric group and unitary groups. And it is my hope that through studying the structure of these measures more carefully, we can obtain deep insights into the structure of multipartite quantum states. Thank you for watching.